Hi, I'm Jeff Groh and this is Differential Equations, Exam 3 Review. We're going to begin with y double prime plus 4y prime plus 29y equals delta 3 of t, y of 0 equals y prime of 0 equals 0. Because we have the Dirac delta function here, we need to use Laplace transforms, which is made simpler because the initial data are all 0. So applying the Laplace transform to the left-hand side, we have s squared times the Laplace transform of y, which is denoted by a capital Y, plus 4s times big Y plus 29 big Y. The Laplace transform of the Dirac delta function centered at 3 is e to the minus 3s. We factor the y out on the left, let big Y times s squared plus 4s plus 29, still equal to e to the minus 3s. Dividing, we have e to the minus 3s. On the right-hand side, we're going to have this divided. Now, completing the square, dividing 4 by 2 yields 2, squared is 4. I kind of wish this were plus 4, but to counterbalance that, it's plus 25. That'll give us s plus 2 squared plus 25. To make this expression look more like something in the table of inverse Laplace transforms, we need to have the square root of 25 in the numerator, or 5. Remember, if this is b squared, this should be b. So I'm going to make this 5 because I get what I want. But to pay for it, I have to put a 1/5 out front. We're now ready to calculate the inverse Laplace transform. The solution is y equals 1/5 u3 of t e to the minus 2 t minus 3 sine of 5 times the quantity t minus 3. On problem 2, I ask you to calculate the Laplace transform of several functions. We'll begin with t cosine of 3t. When we calculate the Laplace transform of a function having a coefficient of t, the effect of the t is minus the derivative of the Laplace transform of everything else. The Laplace transform of cosine of 3t is going to be s over s squared plus 9. Remember, it's of the form s over s squared plus b squared. Calculating the derivative using the quotient rule, we get the derivative of the top, which is 1, times the bottom, s squared plus 9, minus the top times the derivative of the bottom, divided by the bottom squared. You can see now that we'll have s squared minus 2s squared, which is negative s squared. Adding another negative, we'll have s squared minus 9 divided by s squared plus 9 quantity squared. On part B, I ask you to calculate the Laplace transform of 5 delta 2 of t. The 5 can be pulled out of the Laplace transform using one of the linearity properties. The Laplace transform of delta 2 of t is e to the minus 2s. C, I ask you to calculate the Laplace transform of e to the 3t cosine of 2t. Remember that the effect here is to translate by 3 units. And this gives us a plus 4 in the denominator. On problem 3, I want you to calculate the inverse Laplace transform of various functions. On part A, calculate the inverse Laplace transform of 3 over s minus 2 squared plus 9. You can see that we're going to have a sine function here, but with an e to the 2t. So we get e to the 2t sine of 3t. On part B, we have e to the minus 2s times 1 over s squared plus 1. The e to the minus 2s gives us a unit step function centered at 2. The inverse Laplace transform of 1 over s squared plus 1 is sine of t, but we have to translate that 2 units. So it's sine of t minus 2. On part C, I want the inverse Laplace transform of 2 over s cubed. This is the same thing as 2 factorial. So you can see this is going to be t squared. On problem 4, we're solving the initial value problem y double prime plus 6y prime plus 25y equals delta 2 of t, y of 0 is 2, y prime of 0 is 3. Calculating the Laplace transform on both sides of the original equation gives s squared big Y minus 2s minus 3 plus 6 times s big Y minus 2 plus 25 big Y equals e to the minus 2s. If we collect all the y terms together, the coefficient will be s squared plus 6s plus 25. All other terms must go to the other side. That gives e to the minus 2s plus 2s. This is going to be a 3, and we're going to have a 12. 3 and 12 makes 15. Keep in mind that you'd really rather have plus 9. So we can rewrite this part here as s plus 3 quantity squared plus 16, and then divide it off. Dividing, we get big Y is e to the minus 2s times 1 over s plus 3 squared plus 16 plus, we need to work this thing out a little bit. We're going to write it as 2s plus 6 plus 9 over s plus 3 squared plus 16. There's a little more massaging that needs to be done on the right-hand side so that the terms look like the items in the table of Laplace transforms. First of all, since this is a 16, the numerator should be 4. I'll make it so and pay for it with a 1/4 in the front. Since we have s plus 3 here, we really want s plus 3, not 2s plus 15. The way it's been broken up here, this is going to be 2 times s plus 3, and then we'll have this 9 left over. Breaking things up a little more before performing the inverse Laplace transform. We'll have 2 times the quantity s plus 3 over s plus 3 squared plus 16. And one more term. It's going to have a 9 here. I'm going to put the 9 in front. S plus 3 squared plus 16. On this last term, it would be better if the numerator were a 4. I get what I want. I just have to pay for it. So I'll put the 4 there and pay for it with a 1 over 4 out front. We're now ready to calculate the inverse Laplace transform. Applying the inverse Laplace transform of both sides, the solution y is equal to 1/4 u2 of t e to the minus 3 times t minus 2. You have to translate these. And this arises from a sine, so it's going to be the sine of 4 times the quantity t minus 2. The second term comes from a cosine. So that's going to be 2 times e to the minus 3t cosine of 4t. And the last term comes from a sine function. So that's plus 9/4 e to the minus 3t sine of 4t. And that is the solution to the initial value problem.